इसको हटाना है तो कैसे करें?
इसको नीचे कर दीजिए ना, ये मिनिमाइज का ऑप्शन है। अभी छोड़ दीजिए, अभी मत कीजिए अपनी।
वो मिनिमाइज कर दो, कोई दिक्कत। हिंदी वैसे भी उन लोगों को समझ में नहीं आएगी। चलो ठीक है, अब मैं बोल दूंगा। रिकॉर्डिंग हो रहा है ना? तो चलो बंद कर लेता हूँ। Good morning to everybody. So I am very happy to get the opportunity of speaking as a keynote speaker in the second international conference on mechanical engineering and materials, November 19th, 20th, 2021 at Beijing in China. The title of my presentation is Experimental Investigation on AA7075 B4C, that is boron carbide, then ZRC, zirconium carbide, hybrid nanocomposite fabricated by powder metallurgy techniques. So we have done experimental work, and in fact this work has been done by one of my research scholars, G. Manohar. Then content of the presentation, it is introduction, literature survey, research objectives, research methodology, results and discussion, then conclusion, then major outcome, then future scope, then what are the publication out of this work. Then introduction. So what I will state that nowadays composites are one of the major research area chosen by many researchers because of its superior mechanical tribological properties. And among different available matrix material, aluminum is the most preferred matrix which I face due to its exceptional abilities like high strength to weight ratio, then fatigue resistance, energy absorption, then excellent crash characteristics, then corrosion resistance, then wear resistance. Among different aluminum alloys, these 2 XXX, 5 XXX, 6 XXX, and 7 XXX series are in large usage. And it has been reported that among different available composites, aluminum-based composites are now constitute 50% of the Boeing 787 aircraft and 25% of Airbus A380. Then selection of reinforcement particles depend on type of use, density differences in thermal conductivity coefficient, etc. And among different available reinforcements, silicon carbide, Al2O3, B4C, graphite, graphene, CNT are the majorly used ones. Then, to fabricate the MMC, that is metal matrix composites, conventional methods include steel casting, then compo casting, speed casting, etc. But liquid state fabrication techniques have its own limitations due to their processing defects like high porosity levels, poor wetting behavior, non-uniform dispersion of reinforcements, chemical reactions at interface regions, then weak interface bonds, etc. To eliminate these defects, solid-state techniques are recommended, and among solid-state methods, powder metallurgy is the best and economical. And in fact, this work has been recently given a synopsis seminar of one of my PhD students, and I am taking it as it is due to paucity of my time. So I could not prepare separate, and this is the recent work. That is why I am presenting this, and this will show what research we are doing now in our department. Then powder metallurgy, that is PM processing route. So this is the diagram that shows this powder metallurgy, that is matrix, then reinforcement, then ball milling, then composite powder, then composite powder, they are this is spark plasma sintering, microwave sintering, then conventional sintering, and compaction, then sintering, then composite material, then heat treatment. And the cold compaction is there, hot pressing is there, then hot isotactic compaction is there. Then non-conventional sintering mechanisms. So to eliminate major defects in conventional sintering techniques, non-conventional sintering techniques will help effectively. They are microwave sintering, spark plasma sintering. So this is the diagram we can see here. This is the diagram, this is microwave sintering, and this is for spark plasma sintering. Then, in microwave sintering, internal heat generation takes place by the oscillation of dipoles at microwave frequencies. A schematic diagram representing differences between conventional heat propagation and microwave heat propagation are shown in below figure 11. So this is shown here in figure 11. You can see it very well. Then, in spark plasma sintering, heat generation takes place by the generation spark discharges between the adjacent powder particles, produces high temperature plasma, creates strong interfaces with high diffusion rates. Below is the schematic diagram representing the spark plasma sintering. So here we can see these are pulse current, and this is dye and diverted current. So this is thing. Then literature survey. So this is all about what we have done, the literature review. And in fact, I will state that there is a lot of literature available in this area. So I will skip and I will not speak all this because the audience will feel bored about this. All are available at sciencedirect.com. So I will be happy to escape this thing. And our research objectives, they are the following, like fabrication of A7075, B4C micro and nano composite, and the effect of ZRC nanoparticles on A7075 boron carbide nano composite through powder metallurgy technique. Then investigating the optimized volume fraction level of B4C and ZRC in A7075 matrix material. Then effect of different sintering mechanisms like microwave sintering and conventional sintering on microstructural and mechanical properties of optimized volume fraction A7075 B4C composite and A7075 B4C zirconium carbide hybrid nano composite. Then investigating the major differences that occur between the composites sintered through different techniques. Then research methodology, you can see that ball milling is there, then cold compaction is there, then microwave sintering is there, then composite samples we can see here, and mechanical properties, then porosity, then fracture analysis we have done, microstructural investigation we have done, and this is about resultant discussion. So result and discussion. So we should discuss first effect of sintering mechanism on mechanical properties of A7075 B4C composite fabricated by powder metallurgy techniques. That is A7075B4 micro and nano composite and A7075B4C ZRC hybrid nano composites were successfully fabricated. Then firstly, micro B4C levels were varied in A7075 matrix phase from 0 to 8%. Then from the results obtained, it is found that 6% B4C is the optimized volume fraction level in A7075 matrix phase. Then further investigation was carried out by implementing different sintering mechanisms on A7075 6% B4C composite. Then mechanical properties of A7075 B4C composite. So we can see here that is this is the name of composite, then tensile properties in MPa, then compression properties in MPa, then hardness also. So all are given. Then further, A70756% B4C composite was fabricated through microwave sintering and results showed enhanced mechanical properties when compared to conventional sintered composite along with high strength to fracture value. So here we can see the diagram that this is ICMEM images of composite sintered by conventional sintering. This is conventional sintering and this is microwave sintering. So here conventional sintering, this is microwave sintering. So here energy dispersive EDS analysis of composites sintered by different sintering techniques. Then this is microwave sintering intensity, and here this is conventional sintering. So this is XRD analysis of composites sintered by two different techniques. Then conventionally sintered product you can see here, and microwave sintered product. So this is conventionally sintered product and this is microwave sintered product. Then this is figure 4, samples after compression test and percentage of deformation ductility during the compression test. Then next we have studied that is effect of ZRC nanoparticles on microstructural and mechanical properties of A7075B4C nanocomposite fabricated by powder metallurgy technique. So here in this work, nano B4C particles are varied in A7075 matrix material. Then results showed enhanced mechanical properties up to 6% volume fraction level as shown in figure 5. Then thirdly, hardness value keep on increasing with reinforcement volume fraction level. Then further investigation was carried out on A7075 6% B4C level in composite. Then nano ZRC particles were added to A7075 6% B4C nano composite and varied from 0 to 5%. Okay, so I am sorry, after I take a little pause of 5 minutes and I will come again and speak. So I am sorry for this disturbance. So I am sorry, I have gone to my kitchen for preparing some drink for me. So here, this is before C volume fraction, and here we can see the volume fraction of before C, and then tensile strength we can see in the figures, then compression, MPa, and micro hardness also. This is shown with this green color. Then here also these composites are shown, and compressive and tensile strength as versus zirconium carbide volume fraction of the composite, it is shown here. Then short term, this is the name of the composite, and this is short term, this has been used, and this is about micro hardness versus zirconium carbide volume fraction of composite. So what is the conclusion? We have arrived that micro hardness keeps on increasing with ZRC volume fraction. Then this we can see, this figure 10, this is XRD analysis of B ZX. X is equal to 0, 1, 2, 3, 4, 5 up to that percentage and hybrid composites. So XRD analysis, Al3BC intermetallic compound was detected in BZ4 and BZ5. Then this is fractographic analysis. So here we can see that fracture surfaces of A7075 plus 6% B4C plus X% ZRC hybrid nanocomposites, where X is equal to 1, 2, and 3. And then we see that formation of intermetallic compound Al3BC at interface regions beyond 3% ZRC levels was also main reason for degradation of mechanical properties. So along with intermetallic compounds, agglomerates were also observed from microstructural analysis. This represents beyond critical volume fraction material properties is started to degrade. Then from this investigation, it was concluded that A7075 6% B4C, 3% ZRC hybrid nanocomposite gave best mechanical properties. So we concluded like this. Then the third objective was effect of microwave centering on the micro structure and mechanical properties of AA7075 B4C ZRC hybrid nanocomposite fabricated by powder metallurgy techniques. So here, what we have done, that further investigation was carried out on this hybrid nanocomposite by implementing. Now we have done microwave sintering technique, and two composites were prepared by two different sintering techniques. That is conventional sintering and then microwave sintering. And investigation was carried out comparing the both composites in terms of microstructural and mechanical properties. And then from the results obtained, it was observed that conventionally sintered composites showed agglomeration effect along the with oxide layers that we can see from the figures. So we can see from this figure 12. That this is SEM images, same images of A, conventionally sintered composite. B is magnification image of the yellow spot from image 5A and C, agglomeration of ZRC and dispersion of B4C, yellow arrows with ZRC agglomerations, and D, EDS analysis of conventionally sintered composites. Then we are coming to the topic, microwave sintered product shows very little bit agglomeration effect with no oxide layers along with plain surfaces. We can see it from the figure. This is figure 13, and the same images of A, microwave sintered composite, B, magnification image of the yellow spot from 6A showing agglomerates of ZRC, C, strong interface regions of ZRC and B4C with matrix material. Then Al3BC intermetallic phase was present in conventional sintered composite along with this is silicon dioxide. So this is the diagram and this is figure 14. This is XRD analysis of AA7075 plus 6% B4C plus 3% zirconium carbide nanohybrid composite sintered through conventional and microwave techniques. Then this is figure 15, and this shows mechanical properties of AA7075 plus 6% B4C and 3% ZRC hybrid nanocomposites sintered through conventional and microwave techniques. And see, our conclusion is this: from this investigation, it is observed that microwave sintering technique helps in formation of strong interface bonds. Then internal heat generation phenomenon eliminates temperature gradients between core and surface of the particles, resulting in uniform heat distribution while sintering process. Then concluding, microwave sintering is the best for fabricating hybrid nanocomposites. It can eliminate major defects that occur in conventional sintering process and enhances the mechanical properties of the composite material. Then this is about comparative analysis of fabricated composites. Composites reinforced with nano-reinforcement particles showed superior advancement in the mechanical properties of the composite material. Comparing the mechanical properties of the AA7075, 6% B4C, 3% ZRC, nanocomposite with those of the AA7075 B4C, microcomposite, both were sintered through conventional technique, showed an enhancement of 109% in tensile, 81.7% in compression, and 40% in hardness. This showed that the particle size of the reinforcement particle has a severe impact on the mechanical properties of the composite materials. Then additionally, along with nano-range reinforcement particles, microwave sintering helps in enhancing the mechanical properties of the composite materials. Comparing the mechanical properties of the AA7075, 6% B4C, 3% ZRC hybrid nanocomposite sintered through microwave technique with AA7075, 6% B4C micro composite sintered through conventional technique showed an increment of 134% in tensile, 101% in compression, and 55.3% in hardness. Then the main disadvantage is composite material with their low ductility nature after reinforcing with high reinforcement content levels. Present investigation showed that enhanced ductility levels can be achieved by implementing advanced sintering mechanisms like microwave sintering with nano-range reinforcements. Comparing the ductility levels of fabricated composites, A7075B4C ZRC hybrid nano composite sintered through microwave technique showed strength to fracture value of 12.2%, while A7075 B4C microcomposite sintered through conventional technique showed a strength to fracture value of 4.1%. So we are getting a large difference. Well, one place it is 12.2% and the other place it is only 4.1%. Then these are the diagram of tensile strength in MPa, compression strength in MPa, and hardness in MPa. So this is ductility level of composite fabricated in the present work. In conclusion, so the conclusion of our whole work we are giving now. So composites were fabricated by powder metallurgy techniques, and sintering was done by using two different techniques, namely conventional sintering for 150 minutes at 620 degrees centigrade and microwave sintering for 30 minutes at 500 degrees centigrade. Then the distribution of reinforcement in the matrix was uniform in microwave sintered composites and no agglomeration sites were detected. The conventionally sintered composites showed high agglomerations which act as obstacles for effective heat propagation while sintering and act as a pre-existing crack sites, which hinders the effective load transfers between matrix and reinforcements, resulting in material failure at low stress levels. Then comparing mechanical properties of all two composites, composite sintered through microwave sintering has shown superior properties because of its short sintering time and temperature. Formation of AIB, intermetallic phase in conventionally sintered composite makes. Then this porosity levels were drastically reduced in microwave composites, while because of the enhanced diffusion process that forms a stronger interface bond than conventional ones, allowing materials to exhibit superior mechanical properties. Then enhanced diffusion and low agglomeration porous defects in microwave composites helped in the formation of strong interfaces, having high strength to fracture values of 12.3%, which was superior when compared to conventionally sintered composite. What is observed from the results obtained in this research is that sintering techniques having internal heat generations, lower sintering times, and lower sintering temperatures give excellent mechanical property to the composite materials. Then A7075B4C ZRC hybrid nano composite was fabricated through powder metallurgy techniques to investigate the impact of nano ZRC particles on microstructural and mechanical properties of the optimized volume fraction. A70756% B4C nano composite nano ZRC content level varies from 1% to 5% in A70756% B4C nano composite from the results obtained following observations noted. These are addition of nano ZRC powders to these composites, so further enhancement in mechanical properties up to 3% volume fraction of nano ZRC. Further increment of nano ZRC content in A7075 6% boron carbide showed degradation of mechanical properties. Hardness values showed keep on increasing with reinforcement volume fraction. Then next is microstructural analysis revealed that the distribution of nano reinforcement was uniform up to 3% ZRC content level, and further increase in nano ZRC level showed agglomerations of ZRC particles. Nano B4C particle distributed on ZRC agglomerates also showed uniform distribution of B4C particles throughout the material. Then, with the presence of agglomerates from 4% ZRC level, porosity level drastically increased that make hybrid composite weak. Then XRD analysis showed the presence of Al3BC intermetallic compound in AA705, 6% B4C composite. The presence of Al3BC compound showed no negative effect on mechanical properties. Formation of Al3ZR intermetallic compound at 4% ZRC volume results in degradation of mechanical properties of hybrid composite, but this happens at 4% of ZRC. And fracture analysis reveals peeling action of reinforcement particles from the matrix material from 4% ZRC content levels. So we can see that from the observation, it is concluded that the addition of different reinforcement particles beyond optimized volume fraction composite further increases its strength up to some critical limit. Beyond that, composites show agglomerates with high porosity levels along the new intermetallic compounds with weak interface bond that ultimately degraded the mechanical properties of the hybrid composite. And AA70756% B4C and 3% ZRC nano hybrid composites sintered through conventional and microwave techniques were fabricated successfully. Various characterizations were performed to find out the advantage of microwave sintering process over conventional sintering process, and below are the novel findings from the research work. That is, composites processed through microwave sintering showed better mechanical properties compared to conventionally sintered composite. Strong interface bonds in microwave sintered composite led to high hardness values, and low porosity levels were observed in composite sintered through microwave processing, and no intermetallic compounds were generated in conventional sintered composite. Al3BC intermetallic compound was generated, and the presence of impurity layers, SiOT, represent contamination of the interfaces that degraded the mechanical properties of the composite material. Then microstructural analysis revealed that the agglomeration effects in both composites, but microwave processed composites showed better properties indicating strong and clean interfaces, and no peeling action of reinforcement particles from the matrix material was detected in both composites through SEM fractography analysis. It is shown. Then internal heat generation sintering techniques with less sintering times are more suitable and recommended to fabricate nano-range hybrid composites to efficiently use hybrid nanoparticles with minimum defects. Then, major outcomes from the present investigation are the following. That is, compared to composite reinforcement with micro-level reinforcement, composite reinforcement with nano-range reinforcement showed superior advancement in its mechanical properties. Then microwave sintering helps in enhancing the properties of the composite materials when compared to conventional sintering because of its unique features like internal heat generation, low sintering time, and low sintering temperatures. Then it is observed that in microwave sintered composite, no intermetallic compounds were detected, represent clean and strong interfaces. And lastly, from the overall investigation, it is concluded that microwave sintering is the best suited technique for fabrication of hybrid nanocomposites, where there is a high chance of the formation of intermetallic compounds. So future scope of the work is there, and it is given below. Then as added, reinforcement materials are highly resistant to corrosion. Studies on corrosion behavior of the fabricated material may show satisfactory results. Then, the present investigation can also be performed by spark plasma sintering, SPS, and can compare the different sintering mechanisms and the effect of particle sizes on the mechanical properties of the present high-field nanocomposite can be studied. Then lastly, mechanical properties of the composite materials can be investigated with different reinforcement and sintering mechanism combination. Then these are the publications out of this our research work, and here I was the main guide of the student, and one person, Dr. S.R. Mathi, assistant professor in our department, he was a joint supervisor in this project. So we are having many publications, SCI Index Journal, like in Ceramic International, two publications we are having. Then we are having in Silicon Journal also, one paper is accepted and one paper it is published. And in one materials chemistry and physics, that is, one paper is there. And we are having many conference papers, Scopus Index. There are 7 papers out of this work. So I believe that this is good work, and these are the conferences where the papers were presented. So once again, I will like to thank the committee of ICMEM, and I will pray to God that everybody in the world should stay safe and healthy. So this is all about the presentation, and I will say that actually there was some problem in PPT, that is why I made this type of presentation. This is not PPTX. So this is a PDF format on which I presented the thing. Due to some problem in formatting, my laptop was having some problem. So ultimately, once again, I thank the committee of this Second International Conference on Mechanical Engineering and Materials, November 1920, to be held at Beijing, China, for giving the opportunity to speak as keynote speaker. And I will feel very happy to come again to China if any place the international conference is held. And once I went also there to Guangzhou in long before, means December 2019, and after this March, April, this 2020, there was banned due to this corona. So once again, I am very thankful to the audience for hearing me patiently, and I will welcome all the questions through email. So thank you very much for hearing me patiently. Once again, thank you very much. And I am now closing this. Okay, so thank you.